Hi, everyone. Thank you for having me to speak today. And I appreciate you staying up late to be able to catch my talk in many cases. So I'm going to be talking today about BYOC, or Bring Your Own Core, which is a framework that we built during the end of my PhD at Princeton University in order to enable heterogeneous ISA SoC design and research. This is a project that was a big collaboration between folks at Princeton, ETH Zurich, at University of Washington, and some other institutions too. And so we were very interested in the concept of building heterogeneous ISA systems, but why exactly do we want to do that? So, one second, there we go. The norm in the past was that we would build multi-core or many-core systems using a single ISA and a single microarchitecture. But once single ISA heterogeneous microarchitecture systems came along, like ARM's Big Little, we saw that they could offer very big power and performance benefits. And we've now seen them adopted even by Intel, and obviously Apple are big users too. This gives you the opportunity to extend your DVFS curve effectively and get lower power as a trade for lower performance. But we wanted to ask about building heterogeneous ISA. Are there specific benefits to enabling heterogeneous ISA capabilities in multi-core and many-core systems? And so there have been a variety of research in the architecture realm, which had shown that there were actually both performance and energy efficiency benefits to building heterogeneous ISA systems and moving applications between different ISAs as they execute. And there's this great paper from Ashish Venkat and Dean Tulson back in ISCA 2014, where they actually showed that applications have affinities to certain ISAs with respect to metrics that we care about. So energy efficiency and performance, and phases of those applications. So if you look here on the right, there's a chart from their paper that shows that for different applications, you want to spend different percentages of your time on different instruction sets. And whether you care about energy efficiency or performance, you would actually see a different distribution in the time that you should spend. The downside of this prior work was that it was all done in simulation. There were several other studies that were done, and they were largely done in architectural simulators. And under the hood, they assumed that they would have some kind of shared memory capability, but there was no hardware to do this testing on, and they didn't actually go out and kind of build a multi-core processor with this kind of shared memory capability. On the other side, in the operating systems domain, there was research being done to develop operating systems to run across multiple different ISAs. So Popcorn Linux is a very famous operating system in this space, and they had multiple different implementations, including kind of like Xeon server with a Xeon Phi card, or a Xeon server with kind of an ARM SmartNIC or another ARM PCIe card. K2 was another alternative. There's a picture here from the K2 paper where they show kind of the organization of their operating system, where they could run across ARM and Thumb. But there were several downsides to these settings because they had to use existing hardware. So in the case of Popcorn Linux, you had to do this like PCIe-based communication between the host and the PCIe card. And in K2, it was kind of ARM plus Thumb, and they actually used a software coherence mechanism. What we really wanted to know about was, could we build a cache coherent heterogeneous ISA system in order to realize the benefits that architects had proposed could exist, because we weren't able to identify those necessarily with the operating systems that were being built with the hardware that did exist at the time. And so what we developed is a system called Bring Your Own Core, or BYOC, which has the innovation that we can connect a variety of different cores into one open source system. Previous open source memory systems generally only allowed cores of one ISA, and even commonly a single microarchitecture. They're designed to cluster one particular core. In contrast, to date, we've connected more than 15 different cores with 6 different ISAs into this single memory system, which shows the kind of broad flexibility. And our contributions here are building this open source cache coherent memory system explicitly for building heterogeneous ISA systems. We introduced a new core interface to make this possible. You can imagine that you couldn't just bring any arbitrary core and plug it straight in without some modification. We also built what we believe is the first open source general purpose heterogeneous ISA processor. And what we believe is the first open source SMP Linux booting RISC-V Manycore processor too. And you can see the picture here on the right. What we built and provide is this BYOC memory system within the orange box. And people can come along and they can implement the interface and plug their cores into it. Now, today there are a lot of open cores to build with. During my PhD, we were developing the OpenPython platform, and that started back in late 2013. And there really weren't many open cores back then, so it's really exciting, the proliferation of open source cores. And so we want to be able to kind of bring out as many of these as possible and be able to make use of them. And so we started from OpenPython because that's what we had developed in our group. But it had some downsides and difficulties in terms of how to connect things. The system previously only supported OpenSpark T1 core. And so there were kind of a variety of Spark specific specializations in the system. There was this particular bus that was used to connect the Spark core into the coherence system. And so we wanted to answer, like, how can we actually connect other cores and how can we support other ISAs that have very different needs from what Spark had? And so we identified several different options of how to connect cores into the system so that we could provide an IP that others could come along and connect their cores into. And one of the key priorities here was to minimize the effort of that connection, right? We want to have as many cores in the system as we can support and then allow people to mix and match them with different Manycore architectures, different ISAs to see what the benefits would be. And so we kind of identified three possible ways of providing a package where people could do this. The first of these, call here option A, you can see, provides 3 levels of cache in the orange box. And that includes the L1. And so the user would bring their core and they would replace their L1 with one provided by the system. And then they would kind of connect their core that way. Now, this isn't really a great solution. We didn't want to do this. And so we didn't take this option. Specifically, the point before the L1 cache has to be quite coupled to the core's microarchitecture. It has to be very high performance, low latency. And so we thought this would be kind of too difficult to be able to flexibly connect different cores. And people don't really want to throw away stuff they already built, right? So you tell somebody they have to tear out their L1 cache, they're probably not going to want to do that. The second option that we considered was providing simply a last level cache. And then the end user would bring along their core with its L1, and either they would implement the rest of the coherence protocol within their L1, or they would add another layer of cache to implement the rest of the coherence protocol. We also didn't think that this was a particularly good idea because implementing coherence protocols is notoriously extremely hard to do. Our OpenPython coherence mechanism called PMesh has 30 different coherence message types. And it's very likely that people would make subtly incompatible implementations. They would be very slightly different, or they would have different bugs, and it wouldn't be possible to do the integration. So we instead settled on what we call option C here, which is that we provide 2 layers of cache, a last level cache and a local private cache. And then the end user can come along, and if they have an L1, they can bring that with them. And if they don't, it doesn't matter. We'll provide the interface where the black dotted line is here. And so this is lower kind of an easier latency and easier bandwidth requirement than connecting before the L1. It also incorporates most of the coherence system details into the 2 layers of cache that we provide and decouples the users from having to think about those details. And so what we defined was this new interface, the black dotted line here, which we call the transaction response interface, or tree. This is a backronym. It was named for my old groupmate Tree. And this is designed to be a simple interface in terms of the number of message types that you can implement. You can implement just kind of a very small amount and get going and be able to have a core operate. Extensible in that you can choose which subsets to implement based on the functionality that you need. So if you don't need a full Manycore operating system capable design, you don't need to go and implement everything. And then also low overhead in terms of kind of the complexity of the state machines and the wiring and so on to connect your new cores. So we've connected, as I said, many different cores, about more than 15 at this point. But they all implement kind of different subsets according to their needs. And so in the case of the OpenSpark T1, that came with OpenPiton. In the case of Ariane, which is first class supported core, and then our collaborators at the University of Washington have been connecting the Black Parrot core. They implement all of the subsets, and you can actually go out and build Manycore designs based on all three of those cores in OpenPiton, in BYOC, and make use of them. And you can mix and match cores. But it's also the case that some other cores don't need all the capabilities, and so we've prototyped implementing just some of these. And you can see here we even had a Google Summer of Code student who implemented x86 support with a 486 clone. We've worked on microwatt open power. And we even worked with a team at Xilinx to connect QEMU so that you could potentially connect a software-based emulation into simulation and be able to test out other ISAs that we don't already support. As a proof of concept, kind of the very original proof of concept that we developed to show that this would be possible, we built what's called JuxtaPiton, and we believe this is the world's first open source general purpose heterogeneous-ISA processor. It has a 64-bit OpenSpark T1 core and a 32-bit P-core v32 core, which are able to coherently share memory through the BYOC PMesh memory system that we're providing here. And you can see that both of the cores use the same interface, this transaction response interface, to talk to the coherent system. And here, the OpenSpark T1 is able to offload its RISC-V 32-bit binaries to the lower power core. And we built actually all of the software infrastructure needed so that you can do / on a RISC-V binary, and rather than it just throwing an error, it would transparently move the binary over onto the RISC-V core, execute it there, and then that core could actually ask for syscalls to be proxied back to the OpenSpark core. And we could do all this within Linux, right? We could put this on FPGA and show these demonstrations. And so this is actually already open source as part of OpenPiton. You can find the code online and reproduce this. But this was really just the first taste of what we would be able to do. And the paper has kind of more details on characterization of memory system latency and evaluation and so on. So with this, we realized that, hey, maybe we can actually connect more complex cores and build kind of an OS-capable platform. And so we started out a collaboration between the team that we were in at Princeton University and the ETH Zurich Pulp platform team. And our goal here, in terms of what this particular product that we were building, was to make a permissively licensed Linux-capable Manycore research platform based on RISC-V that we called OpenPiton plus Ariane. And we were starting from two really mature and extensible designs. Ariane was already able to boot Linux as an RV64GC core. OpenPiton was, we taped this out and had, a 25-core chip using Spark. And so we were bringing this stuff together with this new interface, this transaction response interface. And we were actually astonished by how well this worked. So we worked together part-time, kind of basically one or two of us, where we're able to get to the point of booting SMP Linux in less than 6 months on FPGA. What was really crazy was that the first day that we did the first Linux boot was single core. That was the Monday. The Tuesday, we did dual core. The following Monday, we did quad core, and we didn't change any of the RTL in between. The validation actually carried across with the memory system from the original Spark implementation with the new additions for RISC-V. And in building this, we believed that at the time, this was the world's first open source SMP Linux booting RISC-V Manycore. So what were the changes we had to make this possible? So you can see here an OpenPiton tile with the Ariane core, and on the left you have the core, and then on the right you have the PMesh coherent system. And so in the core itself, we implemented a new write-through cache subsystem in place of the existing write-back L1s, and that had to support invalidations because it was previously a single core design. And then we implemented the transaction response interface. We also implemented RISC-V atomics into PMesh, right? So we had to have the load reserve store conditional atomics in the L1.5 cache, and we put the fetch and op swap atomics into the OpenPiton L2 cache. And this is generally a good idea for helping with high contention atomic operations. And you might say, well, oh no, they changed from write back to write through. Actually, they found that this was a higher performance cache interface, and that they were able to stamp out bugs that existed with write back in the edge cases because the write through was simpler. On top of this, on our chipset, we had to add the necessary RISC-V peripherals, boot ROM and so on. The boot ROM is actually auto-generated, so you can specify your BYOC configuration, your OpenPiton configuration, and it will produce a device tree that will store in the boot ROM that can then be used by Linux and so on. And so we've actually since then been able to get a port of U-boot, which was upstream. So I think we're the first open source platform to be supported in U-boot. And so we can do a completely standard RISC-V boot flow with this. We also have a compliant debug module, Clint and Plick for debug and interrupt control. Now from here, what was the heterogeneous ISA system that we could build? Well, what we built was a proof of concept that we called Dicho, short for dichotomy. And this was where we had a 64-bit OpenSPARC T1 core and a 64-bit Ariane core, and they could live alongside each other in this cache coherent system, right? So they both implement the same interface into the same memory system, and they're instantiated together into one SoC. We had fully hardware coherent shared memory as a result, and we had the ISA-specific atomics, both for SPARC and for RISC-V, and so the cores could actually synchronize with each other in shared memory and perform work together collaboratively, despite running different ISAs. We could boot separate independent Linux kernels, one for SPARC and one for RISC-V, go through the boot process, and then run user mode Linux applications on top, which could share memory across the two cores, across the two ISAs, across the two kernels. The paper has a characterization of round trip latency and throughput between these two cores. I would normally show a video, but it doesn't come through very well on Zoom, where we actually boot Linux on both of the cores at the same time. Then we can run a program on each core, and they will synchronize up and be able to, use a kind of a bounded buffer to communicate between the two. And we could do kind of more complex work. So this is really the basis to enable us to go off and do the systems research on how to build operating systems with shared memory for heterogeneous ISA systems. We did a full artifact evaluation for this, and so we got 2 badges on that paper. And the prototype is actually available on GitHub too. So you can go and download all the code for this and reproduce it. In sum, what I really want to get across here is that we want to give all of the cores the same features, regardless of their ISA, as far as possible. And that's something that we've largely been able to do. We can connect all these different cores, can build different kinds of Manycore designs. We also actually prototyped an ISA-agnostic hardware transactional memory system, which was pretty cool. And we include accelerators that you can also use off on the chipset in the design. And this is part of a broader effort to build OpenPython and build a PMesh coherence system. And so if you have other cores and you're interested in connecting them, I'd be really happy to talk to you about that, or you're interested in any of the use cases that might come from this. We're really excited about the potential to build heterogeneous ISA operating systems. We're really excited about building more complex and more interesting heterogeneous Manycore SoCs. So with that, that's all I'm going to say here, and I would be happy to take any questions that you may have.